Hello, my name is Abiodun Hanifa. Today, I'm going to be talking about the synthesis of alcohols. In organic chemistry, when we talk about the synthesis of a compound, we're basically talking about how the compound is made. And this usually involves the transformation of the different functional groups that are present in the starting material to the functional groups of interest. So today, we're going to be seeing how we're going to be transforming different functional groups that are present in the different classes of organic compounds to alcohols. And so I have listed on the board different compounds that we can transform to alcohol, from alkyl halides to alkyl to aldehydes to ketones to acid chloride and esters to carboxylic acid and to ethers. So we're going to be subjecting this different class of compounds to different reactions, and we're going to see how we're going to convert all of them to alcohols in different reactions. In organic chemistry, the compound to be synthesized is usually called the target molecule. And so, throughout this lecture, our target molecule is going to be alcohol. And no matter how simple or complex the target molecule might seem, the real thing we need to focus on are the other functional groups that are present in the starting materials, just so we can ensure that the reagents that we're going to be using to be doing our functional group transformations are not going to be affecting the functional groups that should be retained in the target molecule. And if we look at the board, we're going to be seeing different arrays of alcohol, from ethanol to grandisol to chloramphenicol to cyclopentanol to cholesterol. They can all be synthesized by functional group transformations of the starting materials. And so in this lecture, we're going to be seeing how we can convert all these different classes of organic compounds into alcohol. And we're going to be diving into that just in a moment. So the first method is to synthesize alcohols from the alkyl halides using the nucleophilic substitution reaction. Rx is used to denote alkyl halides. We can have something like this. And this is an SN2 reaction, nucleophilic substitution bimolecular. And this reaction, it's a concerted reaction. That is why it is SN2. The attack of the nucleophile and the leaving of the leaving group, the halogen in this case, the chloride in this case, happen at the same time. And that is why it is SN2. So in this case, we are forming a primary alcohol. Precisely, we synthesized propane 1-hol. In the same manner, we can have something like this. In this case, we have an SN1 reaction. This is nucleophilic substitution unimolecular. And in this case, the reaction happens one at a time. So we can have this bromide leaving first before the attack of the nucleophile happens. So what I'm saying is that we can have something like this. We can have something like this. We can have the carbocation formed first before the nucleophile comes to attack. Before the nucleophilic attack happens. So this is an SN1 reaction. This is an SN1 reaction, and this is possible because we are forming a tertiary alcohol, and the product we are forming here is this. is a tertiary alcohol, and it's because we started with a tertiary alkyl halide. And as you can see, the carbon atom that is bearing the bromine atom is carrying 3 other carbon atoms, and that is why we say this is a tertiary alkyl halide, and that is why it is able to give us a carbocation that is stable. The next method that we often use in the synthesis of alcohol is the addition reaction of alkenes. If we subject alkene to an acid catalyzed hydration, as in this case, we're going to form an alcohol. In this case, we have a propane 2-ol. And how does this happen? So we're going to have the alkene attacking the protonated water molecule, so that we have this. And this water molecule then attacks this, so that we have this. Let me draw it here. So that we have this. And then excess water molecule attacks this, so that we form this plus H3O plus. So this is how we form the alcohol using the acid catalyzed hydration of alkene. And one thing you will notice here is that we have a secondary alcohol. If we do this reaction in the presence of light or peroxide, we're going to get a primary alcohol. So this kind of reaction is called a Macronuclear reaction. Macronuclear's reaction. And the simple rule of thumb for Macronuclear's addition across the pi bonds in alkene is that the hydrogen, because okay, let's take a look at this together. If we look at this, if we draw everything out, we're going to have something like this: CH3, CH, CH2. When this reaction happened, when this reaction started, we formed this carbocation, and it's relatively stable. And if we draw this carbocation out, we'll see that we have something like this. We'll see that we have something like this. When this attack happened, this got converted to this. With a positive charge there. And this is relatively stable. So you can see that the proton, the hydrogen has increased from here to here. The hydrogen has increased, and the hydrogen actually got added to this carbon. And that is why we have CH3 here. We have this carbon deficient of electron. And the rule of thumb for Markovnikov is that for Markovnikov's addition, the hydrogen will be attached to the carbon atom that is already carrying the greater number of hydrogen atoms. And in this case, look at the carbon atoms that are carrying the double bond. We have this carbon and this carbon. This carbon has 2 hydrogen atoms. This carbon has 1 hydrogen atom. So according to Markovnikov's addition, the hydrogen atom that is transferring to this, that is being picked up by this alkene, should be added to this carbon, so that we have something like this, so that the nucleophilic attack of the water will happen on this secondary carbon, and that is why we were able to form this compound. If this reaction was Anti-Markovnikov's reaction, we would have formed something like this. We would have formed something like this. We would have formed something like this. 1, 2, 3. So the hydrogen atom would have gone to this place, to this carbon, instead of coming here, so that the OH would then come to this place. So in this kind of reaction, whereby we have the addition reaction across the alkyl double bond, and then we have the OH coming to the carbon atom that is carrying higher number of hydrogen atom, or we say that we have the hydrogen atom going to the carbon atom that is having lesser number of hydrogen atom. So we call this one Anti-Markovnikov Anti-Markovnikov's addition. And for anti-Markovnikovs, the conditions are peroxide. You can use peroxide or lights. So this question is common when they ask you that in the presence of peroxides and lights, what kind of addition is going to happen what kind of reaction is going to happen across the alkyl carbon-carbon double bond. So that is going to be an anti-Markovnikov's addition. And an example would be something like this. If you do this kind of reaction, in the presence of boron trifluoride and say hydrogen peroxide and sodium hydroxide, you are going to have something like this. You notice in this case we are having the OH here on the terminal carbon atom. In this case we are having the OH on the second carbon atom. So this is an anti-Markovnikov addition, whereas this is a Markovnikov addition. The first one that we did, it's a Markovnikov's addition. So that is how we make how we synthesize alcohol using the addition reaction across the carbon-carbon pi bonds in the alkene. So the next method that we use in the synthesis of alcohol is through the reduction of carbonyls, and that will be aldehydes and ketones. We can reduce aldehydes and ketones using the catalytic hydrogenation, we can use sodium borohydride, we can use lithium aluminum hydride. This is much more reactive than this, but they both accomplish the same transformation. So in using catalytic hydrogenation, we're basically using hydrogen gas. So let's say we have something like this. So this is a cyclopentanone. If we pump in hydrogen gas in the presence of, say, palladium catalyst or maybe nickel catalyst, we're going to achieve this transformation to form an alcohol. So as you can see, we have formed an alcohol we have formed a cyclopentanol, starting from a cyclopentanone. And we can do the same thing using sodium borohydride or lithium aluminium hydride. Let's see how that goes. So if we are going to do the same transformation using sodium borohydride, of course, we're going to form the alcohol. However, let's say we have something like this. Let's say we have something like this, and then we subject this to catalytic hydrogenation in the presence of nickel catalyst. We are not only going to have an alcohol, we are also going to have the alkene functional group reduced to an alkane. But if we use sodium borohydride, even if we have an alkene in the molecule, it's not going to affect the alkene. And the same thing goes for lithium aluminium hydride. So either we have sodium borohydride or lithium aluminium hydride, they are going to selectively reduce the carbonyl functional group to the alcohol functional group. And how do they do that? So let's take a look at the mechanism, just a summarized mechanism of reduction of carbonyl using either sodium borohydride or lithium aluminium hydride. So let's use this to denote the carbonyl compound. So basically, either the sodium borohydride or the lithium aluminium hydride, what they are doing is that they are delivering hydride into the reaction. So they are delivering hydride. This is hydride here. They are delivering hydride into the reaction. So the hydride is basically going to attack the carbonyl compound, the carbonyl functional group. So the hydride is going to attack this, so that we're going to have this. Let me hold on. Sorry, so we're going to have, let's say we have the, okay, so let me draw everything. Let's say we have the boron, so this basically just gets delivered, and then it's it's a nucleophile that attacks the carbonyl functional group. So it attacks the carbonyl functional group, so that we have this. We have the alkoxide form. So we formed an alkoxide, and the alkoxide is going to pick up a proton, possibly from water molecules in solution. So it's going to pick up this proton, and this goes this way. So we form the final product, alcohol. So that is how we form the alcohol. And one thing you should take note of is that if we start with aldehyde, we're going to form a primary alcohol. If we start with a ketone, we're going to form a secondary alcohol. So basically what we're saying is that if we have something like this, and let's say we have something like this. So if we have something like this, if we reduce this compound, we're going to form a primary alcohol. 1, 2, 3. But if we reduce this one, we're going to form a secondary alcohol. So we're going to form a secondary alcohol. And we all know what a secondary alcohol and a primary alcohol is by now. So this one, number one here, number one with a degree symbol here is used to denote a primary alcohol, and number two with a degree here is used to denote a secondary alcohol. So basically, in the reduction of carbonyl compounds using either sodium borohydride or lithium aluminum hydride, we are basically delivering hydride into the reaction mixture so that the hydride can then do a nucleophilic attack on the carbonyl carbon, which then generates the alkoxide, and then this picks up a proton during what we call proton transfer, and then we form the alcohol. One difference between sodium borohydride and lithium aluminum hydride is that this one is quite reactive. It's really more reactive than sodium borohydride. It's a much stronger reducing agent than sodium borohydride. And as we can see, if we use catalytic hydrogenation, just like I mentioned earlier, we're not going to have a very selective reduction, but if we use this, we're going to have the reduction selectively taking place across the carbonyl functional group. And that is why we often use sodium borohydride or lithium aluminum hydride in the reduction of carbonyl functional group to make alcohol in organic chemistry. So next, we're going to look at the synthesis of alcohol using, oh Lord, I cleaned this one. Okay, I'm going to write it back. So we're going to look at the reaction of Grignard reagents and carbonyl compounds to make alcohols. The synthesis of alcohols can also be achieved through the reaction between a Grignard reagent and a carbonyl compound. And Grignard reagents are formed when we treat an alkyl halide with magnesium. So we form something like this. An example would be CH3MgBr. So this is a Grignard reagent. And if we react a Grignard reagent with a carbonyl compound, we're going to form an alcohol. So we're going to have something like this. And a Grignard reagent. So in a Grignard reagent, the carbon is mostly anionic. And that is because the electronegativity of carbon is much more than electronegativity of magnesium. So I think electronegativity of carbon is around 2.5. That of magnesium is around 1.3. So because of the electronegativity difference, the bond between carbon and magnesium is such that the electrons that are shared between carbon and magnesium are pulled to the carbon much more than they are available for magnesium. So that this compound, Grignard reagents, can actually be written this way. So that we can have the carbon as a nucleophile, such that we can have a nucleophilic attack on the carbonyl compound, and then we can form the alkoxide. So we have something like this. Okay, so this is a methyl group. So we are considering this as our Grignard reagents. So we're going to have this, and an alkoxide. So we have an alkoxide formed. So then the alkoxide can pick up a proton from water to form the alcohol. So we can form the alcohol that way. one thing that is worthy of note in the Grignard reaction with carbonyl compound is that in Grignard reaction with carbonyl compound, we are forming a new carbon-carbon single bond. So we are forming a new carbon-carbon single bond. Unlike the reduction of carbonyl compounds that that also gave rise to alcohol, here we have a new carbon-carbon bond, but in the reduction using lithium aluminum hydride or sodium borohydride, we don't form a new carbon-carbon bond. And one important thing in the reaction of carbonyl compounds with Grignard reagents is that the Grignard reagent is very nucleophilic, and it's also very strongly basic. So this reaction is highly reactive, and so we really need to perform this reaction in an anhydrous condition, and that is because our Grignard reagents is so reactive. It can react with water. It can react with water, the moisture in the surrounding, such that we can have something like this. We can have something like this easily, so that we can form this, an alkane. We can form an alkane easily with OMGBr. And this is not our desired product. What we desire is to form an alcohol by the reaction of Grignard reagents with carbonyl compound to form an alcohol, and not this one. So what this means is that if we are going to carry out this kind of reaction, the reaction must be carried out in an anhydrous condition. Usually we do this kind of reaction in an anhydrous, in a dry ether, or we say, better still, we can write dry diethyl ether, something like this. So this is diethyl ether. So we often use dry diethyl ether as solvents when we are performing the reaction between a Grignard reagent and a carbonyl compound to form an alcohol. So we have seen the reaction between a Grignard reagent and aldehydes and ketones. Now let's see the reaction between a Grignard reagent and acid chlorides and esters. So basically we can convert an acid chloride to an alcohol by reacting an acid chloride with a Grignard reagent. The mechanism is similar, except for the fact that we are in the case of acid chloride, we are using 2 moles of the Grignard reagents, and we're going to see why we use 2 moles of Grignard reagents in the mechanism. So the first mole of the Grignard reagents is going to generate the alkoxide. So we have something like this. And then this comes back, releasing the chloride ion, so that we have something like this. And then the second moles of the Grignard reagents, we attack the resulting ketone, and then forming an alkoxide. I'm using 2 strikes here just to differentiate between this alkyl group and the alkyl group that we're introducing now. So the alkoxide is going to get protonated, and then we're going to have the final products. So this is going to get protonated, and then we're going to have the final products. And that is how we can also convert an acid chloride to alcohol by the reaction of the acid chloride with Grignard reagents. The same approach is used to convert ester to alcohol. The same mechanism basically. We use 2 moles of the Grignard reagents. I'm not going to draw the mechanism for the ester. It's just similar to the mechanism for the acid chloride. So the next thing that we're going to look at is how we can convert ester and carboxylic acid to alcohol. So basically we can have an ester converted to an alcohol. And also we can have an acid converted to an alcohol. In this case, we are forming primary alcohols. As you can see, the carbon bearing the OH group is having just one alkyl group attached to it. So this reaction is a reduction reaction and is usually carried out in the presence of lithium aluminum hydride. In most cases, XX lithium aluminum hydride. And the mechanism is similar to the mechanism that I showed you when we reduced carbonyl compounds using lithium aluminum hydride or sodium borohydride. I'm going to show you now. So we're going to use ester to explain this. So just like in the reaction of Grignard reagents with acid chloride and ester, we used 2 moles of Grignard reagents. So also, if we are trying to reduce ester and carboxylic acid using lithium aluminum hydride, we also need 2 moles of the lithium aluminum hydride. So if we have the ester like this, so we're going to have the hydride coming from the lithium aluminum hydride. Sorry, that should be aluminum. So we have the hydride coming from here. So it's going to attack here, and this is going to go to the host gene, and then we're going to have this intermediate with the hydrogen here. And so this is going to come back, and then we're going to have this as a leaving group. The OR is going to leave, so that we're going to have this. We're going to have an aldehyde, and then the second mole of the lithium aluminum hydride is going to do another nucleophilic attack on the resulting aldehyde, so that we generate an alkoxide. And then the alkoxide is going to be protonated, so that we form the final products, the alcohol. So that is how we form the alcohol using the reduction of ester, and the same thing applies to the reduction of carboxylic acid. So if we reduce either carboxylic acid or an ester using lithium aluminum hydride, we are going to form a primary alcohol. And that is how we are able to form alcohol using the different reactions of different classes of compounds, the aldehyde ketones, acid chloride and ester, by reaction with Grignard reagents or reduction with lithium aluminum hydride or sodium borohydride. So next, we're going to be talking about how we can use ethers to make alcohols. So let me clean this place. So let's see how we can synthesize alcohols from the ethers. Let's say we are trying to convert diethyl ether to an alcohol. We need a really strong acid like hydrogen iodide. So if we subject this to an hydrogen iodide reaction, we're going to have an alcohol. And specifically here, we're going to have an ethanol. So this is diethyl ether. So in the presence of this strong acid, hydrogen iodide, we can protonate this diethyl ether so that we have something like this. Let me draw this out. So we have something like this. Oh, sorry, this is iodide. So we have something like this. So this can pick up this proton, and this goes on the iodide. So we have this. So we have this. Or let me draw it like this instead. And we have the iodide ion in solution, which is a strong nucleophile. So this iodide ion can attack this in an SN2 reaction. It can attack this carbon, and then the electron here can go on the oxygen atom, so that we have the products. We have the product ethanol plus ethyl iodide. So for this reaction to happen, we'll need a strong acid like hydrogen iodide. And as we can see, it does, after the protonation, the first step is the protonation of the ether oxygen, and then the iodide ion do a nucleophilic attack on the carbon, and the electron here is taken up by the oxygen atom to form the final product ethanol and ethyl iodide, the side product. So this is the products of interest. So we can see here that we form the alcohol from ethers. But one thing that is worthy of note is that if we have excess of this, we are going to have a second reaction happen such that we're going to basically form water and another mole of ethyl iodide. So we have 2 molecules of ethyl iodide and water formed. So for this reaction to be successful, we need just one equivalent. We need just one equivalent of the hydrogen iodide for this reaction to happen successfully. And so that is where I'm going to stop for today. To summarize, we have seen how we can synthesize alcohols from different reactions. So we started out by talking about the nucleophilic substitution reaction of the alkyl halides to form alcohol. We also talked about the acid catalyzed hydration across the alkene double bonds to form the alcohols. We also talked about different reduction methods of the carbonyl compounds to form the alcohol, and also we looked at the reaction of carbonyl compounds with Grignard reagents also to form alcohol. And lastly, we talked about the reaction of the ethers with a strong acid like hydrogen iodide to form alcohols. So basically, we can use a variety of methods to synthesize alcohol, and these are just some of the most common methods that we use in the laboratory to synthesize alcohols, and most of them are also used in the industry, pharmaceutical industry, and anywhere the need for alcohol is paramount. So this is where I'm going to stop for today, and I'll see you in the next lecture. Bye.